Good morning, everyone. Welcome to the second seminar of this Pitch to URI's Analytical Needs series conducted by URI Analytics Cluster. For those who wonder what is URI Analytics Cluster, I would like to give a short introduction. URI Analytics Cluster refers to URI Central Analytical Facilities and a dedicated team who manage these facilities. Currently, there are about 120 central instruments in URI. This number is still growing. You will see more advanced instruments in our labs in a few months' time, including GC triple quad, GC Q-TOF, ICP triple quad, and so on. So some challenging samples that you are not able to analyze at this moment may become possible later on with a new instrument. Right? URI Analytics team is led by Prof. Shen, who is the Executive Director of URI, and Prof. Fang, who is the Deputy Director of URI Analytics Cluster. And it's comprised of 5 people, including myself. By the way, in case you don't know, my name is Kai Yue, and Ellie, and Janelle, and Dai Yu, and Mei Shan. Mei Shan is currently on maternity leave. Yeah. So the most important objective of our team is to provide strong analytical support to the researchers in URI. This includes not only basic training and routine maintenance of our instruments, but also application support, method development, and so on. So as part of this objective, we would like to share the knowledge that we have accumulated through the applications that the team has supported for research projects in URI. For today's seminar, LV will share her knowledge on LCMS sample preparation techniques, manual SPE, and online SPE. I call this a tailor-made seminar because the contents that LV is going to present is really based on the instrument capability and the type of samples that we have in URI. So a lot of tips here are not possible to be found elsewhere. Sounds good? So today's speaker, LV, she joined URI in 2015. She was the first person, the first team member that I recruited after I started this URI Analytics team. She graduated in LCMS in NTU as a first class honors. I still remember during the interview, one prof said it was such a pity that she doesn't want to do PhD with us. Anyways, she has done a very good job in URI. Yeah. Prior to joining URI, she worked as a research scientist in AMRI, which is a global contract research and manufacturing company specialized in drug discovery and development. Her job role now in URI focuses on chromatography and spectroscopy instruments, including LCMS, GCMS, FDIR, and Raman. Right? So without further ado, let's begin the seminar. Good morning, everyone. So I'm LV from URI Analytics Cluster, and thank you so much for joining us today. So before I start my presentation, just to let you know, we prepared some biscuits and snacks, so please feel free to get some during the presentation. So today's topic is LCMS sample preparation techniques, especially on manual SPE, solid phase extraction, and online solid phase extraction. So the next slide, let me go through the agenda. First is, so why do we need to do sample preparation? And what are the sample preparation techniques that are most suitable for our samples here in URI, such as filtration, liquid-liquid extraction, manual solid phase extraction, and also online solid phase extraction. Let me bring you to the next slide. So why do we need to do sample preparation? Isn't it very difficult and isn't it time consuming? But we all know
that our sample here in URI are actually very heavy in matrix, and then the analytes are not sensitive enough to be analyzed by our instrument. So the concentration of those analytes that we are interested is actually too low to be measured. And also, because of the heavy sample matrix, right, it will cause the ion suppression or enhancement, which I will actually go through with you with some examples, real examples that we have here in URI. And of course, our samples are kind of wastewater sludge, which has a lot of particulates. As you can see, we have some dirty samples here. So it's very important to actually remove those particulates. It may cause blockage to the instrument, and it also can damage the column. So these are all costs to us and to the users. And of course, very important is this complex sample matrix. We'll also dirty our ion source capillary. This example here is basically the spray shield of our LCMS. If our samples are too dirty, not well prepared, then it will dirty our ion source, our LCMS. In turn, it will lead to instrument downtime. So all of this is not good for us. Okay. Next, these are the examples. So what do I mean by the analyte concentration is too low? Over here, I'll be comparing chromatograph for this compound, ciprofloxacin, which is basically an antibiotic. So we analyze this here in ABC. The first example at the top, these are in a wastewater samples at 25 ppb without any sample prep, without any solid phase extraction. You can see that in this chromatogram, basically there is no proper peak being observed, and there are so many background noise over here. So we cannot quantify this compound properly. But at the bottom, we have this 0.5 ppb of the same analytes, and then we go through a night SPE. We could able to see a proper and nice peak, and we could identify this peak properly. So if I overlay the two chromatogram, you can see such a big improvement with a proper sample prep. So in this case, after you go through any sample preparation, for example, online SPE, we could able to detect this compound. The next example will be on the signal suppression or enhancement that is actually caused by our sample matrix. Okay. So I'm comparing analytes in just water and wastewater samples. The black color one will be the chromatogram for analytes in water. As you can see in this example, the signal of this compound, this TCP, which is also commonly detected in wastewater samples, the signal of this compound in wastewater is actually much lower compared to the signal in water. So this basically shows that there is a signal suppression for this compound due to the heavy matrix. And the next one will be a diclofenac, also usually detected in wastewater. However, in this example, there is a signal enhancement occurring. So as you can see, this color, the pink color chromatogram has a higher intensity compared to the intensity in water. So this basically just shows that heavy sample matrix will cause signal suppression and enhancement, which in turn lead to a false positive or false negative. Okay. Now we will go through one by one what are the suitable sample preparation techniques for us in URI. Okay, first step is the filtration. So why do we do filtration? To remove the solids. And then how do we do that? We can either use a filter unit. So we have this over here. Basically, this is a filter unit suitable for a large sample volume, and the filtration will be done by the vacuum pump. Or you can also use a centrifuge. So basically, you spin down your sample, and then those particulates should suspend at the bottom, and you take the supernatant. And then the next one, you can try syringe filter. So this will be straightforward, but make sure that you choose the right syringe filter. Okay. So filtration looks very straightforward, isn't it? But of course, we also encounter some problem during this filtration. For example, the filtration is too slow. So what happens is our wastewater samples or sludge samples has too much particulate. So when you filter, actually at one point it will become too slow. What you do is you could try to those particulates has already covered the membrane, then whatever your sample cannot go through. But of course, if it doesn't work anymore, you can always consider to change a new membrane. And the next one would be, so what about samples that cannot pass through the stage filter? Have you experienced this? You're trying to filter your sample, but somehow you cannot get your samples through? Anyone? You know why actually we cannot get the samples through the stage filter? We have USB for you if you attempt to answer. It's like 8 GB USB, so not bad. No one?
The sample too dirty, and then maybe the pore size is too small.
Okay, that is a valid answer. One for you. Yeah, that's true. Another reason is probably because your filter, you have not chosen the right filter. So sometimes because our sample is mainly aqueous, so you need to choose a hydrophilic filter. If you pass your samples through hydrophobic filter, actually it will not go through. Yeah, so this is important. Okay, the next one will be liquid extraction. Some of us here are actually doing a liquid extraction prior to the LCMS. So what is actually a liquid extraction? Okay, I have a very long explanation over here. Obviously, it's from Wikipedia, right? But basically, liquid extraction means you are trying to extract your analytes from your liquid sample using some other solvents, which is immiscible. So make sure that the two layers are immiscible, and then your analytes must be soluble in the organic solvent that you have chosen. So let me just bring you through steps-wise of this liquid extraction. Okay, what we have over here, this is actually a separating funnel. So it's a general setup that we have over here in URI. And imagine that your sample is a 50 ml, and our sample here in URI is basically aqueous samples. So you just add those aqueous samples into the separating funnel. And then depending on what kind of analytes you want to analyze, you have to add a certain amount of the organic solvents. In this example will be dichloromethane. So after you add, make sure that you must shake well the separating funnel, and after that you should be able to get 2 layers like this, and you must drain the dichloromethane to another flask. So in this case, dichloromethane has a higher density than your aqueous sample, so that's why it's actually at the bottom and you will be able to drain it. After that, you have to repeat the same steps for at least 3 times, because what you want to do is to try to extract as much as possible from those analytes from your samples. So after 3 times of extraction, combine all the organic layers that you have, and then you need to add sodium sulfate. This is actually a drying agent, so you need to remove small amount of water that may have gone into your organic layer during the extraction. The next step would be you have to filter off all the sodium sulfate, and then you have to evaporate to dryness. So it may sound simple and straightforward, isn't it? But sometimes in liquid extraction, actually we do encounter some issue. The most common one would be emulsion. So emulsion may be formed during the extraction, as you can see in this example. So this is basically sample with dichloromethane, and you can see these are actually the emulsion that is formed. The 2 layers are not separated properly. So what do you do? This next example is actually after the 2 layers are being resolved. So for this, what you can do is to add water. You add water to the whole setup, and then this water will add to decrease the density of the top layer. So in liquid extraction, actually what are you trying to do to remove the emulsion is try your best to separate the 2 layers, get the density of the 2 layers to be a lot different. So addition of water, or in some cases addition of sodium chloride may help. Okay, so this will be the manual solid phase extraction, which is the main focus of today's topic. Please listen up. Okay, solid phase extraction. So again, what is solid phase extraction? Again, I have the definition from Wikipedia for you. But basically what we are trying to do over here is you have your liquid samples and then you will load it on a solid cartridge, and then those analytes must be retained in your cartridge and then dilute according to what you want. Sounds complicated? It's okay, I'll explain to you. Sequence of solid phase extraction. So first step is, okay, this cartridge, this is actually a solid phase extraction cartridge that we usually have. First step is to condition the solid phase cartridge, because the cartridge itself has a dry packing material. So the dry packing material, you need to activate the material first before you actually load your samples. This is especially important because, especially for the C18 based packing material. As you can see, this is after the solid phase extraction is conditioned well, so the packing are actually being expanded. But at the dry state, right, all the C18s is actually packed together. So when it is packed together and you didn't condition properly, your sample will not be able to interact later on with this packing material. So proper conditioning is important. And after you condition with your solvents, the next step would be to replace the solvent with your sample solvent. Of course, in this case, your sample is actually in aqueous, so water. So usually we will equilibrate the cartridge. Same step, you load the water, and equilibration is to basically replace whatever solvent that you have added into the SB cartridge. Then after you finish equilibrating the cartridge, you need to load your sample. So please load your sample into the cartridge, and we need to allow sufficient time for the sample, for the analytes inside the sample to interact with your packing material. Your packing material will be over here. So make sure that it's enough time to interact, and the analytes that you want should be retained inside the cartridge. Next step. So next step would be you need to actually wash the packing material, because remember, when you load your sample, not only your analytes of interest will actually retain inside the packing material. Your matrix, your high matrix interference will also retain, some of it at least, will retain inside the packing material. So you need to choose a proper washing solution to remove those interference from the cartridge. So this is the washing steps. And this is the drying step. So drying step is optional. However, it's recommended because this drying step with nitrogen, it will actually help to break the interaction of your analytes with the packing material, so that later on, during the elution, you will get a better recovery. So last step would be to elute the compounds. So you choose according to what kind of analytes you want, and then elute those interests out from the SPA cartridge. So these are basically the steps for a solid phase extraction. Okay, so what are SPA cartridge retention mechanism? We have a few here: normal phase, SPA cartridge, reverse phase, and also ion exchange. In the next slide, I'll show you the summary of the cartridge selection. Okay, these are all the summary. I will not go through one by one, but what I want to show you is here under the sample matrix. So basically for Nuri sample which are highly aqueous, usually we will use either reverse phase or ion exchange. So again, how do you know whether you use a reverse phase or whether you use an ion exchange cartridge? So you have your sample. First that you need to ask yourself, are you doing a targeted analysis? Do you know what you want to see or what you want to quantify? Or you have you don't have any target, so you just want to do unknown analysis. So when you have your targeted analysis, you also need to find out, are those analytes that you want to see considered as basic analytes, or acidic, or neutral? So if it's basic, of course, you should go to the cation exchanger solvent. If it's acidic, select the anion exchanger solvent. However, if it's neutral and it's unknown analysis, as a rule of thumb, you can try to go to reverse phase cartridge because it will cover a bigger range of compound. Okay, now on the optimization tips of this solid phase extraction. So the first two steps, which is the condition and equilibrate, these two are not flow sensitive. However, if you can condition the cartridge properly and equilibrate, it's very important to get a higher recovery. So the next three steps, which is the load, washing, and elute, these three steps will be flow sensitive because basically you need to have enough time for your analytes to interact with your packing material, and then during the washing also, you must make sure your washing solution enough time to wash those interference from your cartridge, and during elution, your solvent of choice must have enough time to extract those analytes and then elute it out from the packing material. So for these three steps, you can always start with drops flowing from the device, usually 1 ml per minute. Then you also have to check the recovery. I will go through how to calculate the recovery later on. And after that, you have to do some experiment, controlled testing to a higher flow rates, because in our samples over here, you may not just be dealing with like 5 ml, 10 ml. You may also just load 250 ml, which is a big volume. So sometimes you need to do the testing. You need to balance between the flow rates and the optimum recovery. And the last step would be to dry down your elute and then reconstitute before LCMS analysis. So if you have no idea, you have just started on the SPE, what would be the recommended SPE method? So our colleague over here, Anumo, he has developed this SPE method for analysis of over 30 compounds, including pesticide, PPCP, and they also use wastewater as their sample matrix. So you can always try this first. First step is to condition with 5 ml of MTBE, methyl tertiary butyl ether, followed by 5 ml methanol, and then equilibrate with 5 ml of water. Load your sample and then wash with water. Dry the cartridge with nitrogen flow for 30 minutes, and then elute with 5 ml of methanol, followed by 5 ml of 10 to 90 methanol MTBE. And the last step is to dry down to less than 0.5 ml and then adjust it to 1 ml with methanol before your LCMS analysis. So you may note that there is this use of MTBE, which is not commonly found in SPE method. So basically, the researcher is using this MTBE because of the allotropic strength. So it acts to cover a bigger range of compounds. However, if you decided to use this recommended SPE method, it's very important to dry your cartridge completely under this step before the elution. Because what I actually encounter myself is that the emulsion formed during elution because I did not dry the cartridge properly. So what you will see over here is something like this. There's 2-layer form. But what you want is actually something like this clear solution after elution. So the reason is because the cartridge was not properly dried before the elution steps. And then MTBE is immiscible with water, so you will get this problem if you did not dry your cartridge. Okay. Nano SPE. So this is just a show of what we have here in URI. So we have this SPE vacuum manifold, either for 12 samples or 24 samples. And then how do you condition, equilibrate, load, wash, and elute? All is by the essences of the vacuum pump. And this is suitable for a small and large sample volume. However, the issue would be it's difficult to control the flow rate. And these two are the common cartridge samples that we use. So you can use either one. The difference will be just on the adapter over here and the adapter over here, but both works well. The next one would be the setup, another setup that we have here. So these are actually a peristaltic pump. So you can connect the peristaltic pump to your sample. And then this is suitable for large sample volume. So you can just put your tubing into the portals and then you just flow through. The good thing is you can always set the flow rate so it's controlled. However, you can only connect one peristaltic pump to one sample. So these two setups are actually, you can use either one as long as it's suitable for your samples. Okay, now we'll go through the recovery. So how do you actually check whether your SP method is good enough? You need to actually do a matrix spike recovery. So there's two experiments over here. First would be your sample with analytes. Basically, it's just your sample matrix. So you load 5 ml of the sample, and inside you should have some little amount of analytes. You do let it go through the whole SP process, elute, evaporate, and then reconstitute. When you analyze in LCMS, you will get certain XPBB. While in another experiment, you spike the samples. So with the same sample matrix, you just spike a certain amount of analytes that you want to detect. For example, in this case, the spike amount is 2 nanogram. And then go through the whole SPE, elute, evaporate, reconstitute, and analyze by LCMS, you will get YPBB. So in this case, please note that you know exactly the amount of spike analytes. Let me just go through. So the spike amount over here after we calculate will be 2 nanogram, and you reconstitute it to 1 ml. So essentially the spike amount after the whole process inside the vial, theoretically, it will be 2 ppb because it's 2 nanogram over 1 ml. So how do you calculate? The SPA recovery is calculated by comparing the concentration of the spike sample with the concentration of unspiked samples. And make sure that both the extracted samples must be in the same solution. And this would be the equation. Percent recovery would be the concentration of B, which is the sample that you did the spiking, and concentration of A is just the sample matrix, divided by the known spike concentration, which we calculate just now as 2 ppb, times 100%. So in the previous example, the calculation will be shown here. Do you get what I mean? I hope you do. You may get a bit confused, but later on when you get back to the slides, you can slowly look through the details. The next will be the matrix effect. So this is also one of the important subjects in solid phase extraction. Again, you will do a 2 experiment. Over here for the matrix effect calculation, we usually use it with internal standard, which is isotope labeled. So first experiment, just spike water with internal standard, and the next one will be sample with internal standard. So same amount. And then what you do is you go through the whole SP process, elute, evaporate, and reconstitute into 1 ml. How to calculate the matrix effect? By comparing the peak area. Peak area of this isotope label standards in sample matrix and in ultra pure water. So this will be the equation. Percent of matrix effect would be peak area in the water minus peak area in sample matrix divided by peak area in water times 100%. So in this equation, please note that a positive value indicates a signal suppression and a negative value indicates a signal enhancement. So you have to take note of this. Okay, the next one would be online solid phase extraction. So some of you may have known that we have this online solid phase extraction directly coupled to LCMS. So what we have over here, this is basically the LCMS that we have in the lab. Over here would be the column compartment where you install your column. And then this is the flex cube. Multi-sampler. At the moment, the multi-sampler maximum injection volume will be 900 microliter. And at the right side, this will be the LCMS itself. So which part is actually the online SPE? This is the online SPE, which we call it as a flex cube. So in this example, we have a 10-port valve, and we are able to install 2 online SPE cartridge. We have a piston pump over here, and the cartridge will be these 2. So the online SPE cartridge are basically already installed in the system, and we can have 2 cartridge over here, which you'll be able to run your samples alternately. Okay, the next one is I'll show you the video on how online SPE works.
Your analytes, remove matrix components or lower detection limits for trace level water analysis. The highly modular design of the Agilent 1200 Infinity Series online SPE solutions provides you with the flexibility to tailor your system to match virtually any analytical LC challenge. Agilent's online SPE solutions are based on the 1290 Infinity Flexible Cube that houses up to 2 valves and reusable SPE cartridges. Valve heads are easy to mount on the drives, thanks to Agilent's quick change valve technology. The flexible cube also has a built-in piston pump and a solvent selection valve for conditioning and loading the cartridges. Combined with Agilent's 6400 series triple quadruple mass spectrometers, this online SPE solution takes you into a new dimension of ultra-low level detection with straightforward turnkey operation. An extensive portfolio of valves makes it easy to customize your online SPE system to fit your needs. Combine these kits with the SPE starter set for applications such as direct injection, multi-SPE, high volume injection, or flask sampling. The starter set opens the door to endless online SPE possibilities with a 2-position 10-port valve mounted in the flexible cube and connected to 2 SPE cartridges. The flexible cube's built-in piston pump and solvent selection valve allow you to condition the first cartridge with up to 3 different solvents. In parallel, the second cartridge is in the analytical flow path. After injection, the piston pump is used to deliver up to 1.8 milliliters of sample onto the SPE cartridge to enrich the analytes of interest, while the matrix constituents, such as salt, are flushed to waste. When the sample has been loaded, the 2-position 10-port valve switches to the elute position, and the LC pump extracts the enriched analytes from the SPE cartridge for separation on the analytical column and detection with a triple quadruple mass spectrometer. Expand your application possibilities further by adding the direct injection.
Okay, I will stop here because what we have is actually the SPE starter kit. So, can I check whether you get what they say? How many SPE cartridge that we can actually connect to the online SPE? Anybody? Who said it?
2.
2? Yes.
Thank you.
Yes. So we can actually install 2 SPE cartridges on the online SPE, and then it will work alternately to prepare our samples. Right, let me just go through with you again. Basically in online SPE there's 2 positions, load position and elute position. So in load position, what happens is this piston pump will load your sample into the first SPE cartridge over here, and then we also have the LC pump which works for the LCMS, and the LC pumps will pump through the solvent through the second SPE cartridge, and then it will go to equilibrate your analytical column, preparing for the analysis. And the next one would be the elute position. So in elute position, the valve will actually switch, and when it switch, what happens is your LC pump will elute your sample from the first cartridge. So your first cartridge was already loaded with your sample, and then now the LC pump will elute those analytes from this, whereas your piston pump will prepare the SPE2 cartridge and equilibrate it, prepare it for the next injection of your sample. So it works together. So what we have during OSPE method, would be, we have two. We have a flex cube method and also LCMS method. So you need to set the method for the online SPE in your software, and then you need to select the method, the mobile phase analysis of your LCMS. Okay, so this is the general online SPE method under the flex cube. There are a lot of details, I will not go through with you. But what I want to show is over here, a 12 minutes method will be good enough to actually clean up your sample under the online SPE and then inject to your LCMS for the analysis. So sounds good, right? It's actually quite short. Okay, so how do we actually optimize this online SPE method? So of course, first thing, you must select the proper cartridge. So even though online SPE cartridge is not as much as the normal manual SPE, but the selection should be good enough for those analytes that we have in URI. And the next would be, you have to play around with the loading flow rate. So typically the loading flow rate for this online SPE is 1 ml per minute. And if you go for a higher flow rate, let's say 1.5 ml per minute, what happens is basically your analytes may not have enough time to interact with your cartridge. Whereas if you use a lower flow rate, like 0.5 ml per minute, then what happens is you're actually extending your analysis time. So again, you need to find a balance between the analysis time and also the recovery. Next one will be the sample loading solvent. So typically, to load your sample into the online SPE cartridge, you will use a highly aqueous solvent, simply because your sample will be an aqueous sample. And then the next one is the loading time. So you need to check for any analytes breakthrough. In this case, for the loading time, for example, you set 3 minutes of a loading time. And just now we say that the optimized flow rate will be about 1 ml per minute. And if you remember, I told you earlier that our multi-sampler has a maximum injection volume of 0.9 ml. For an injection of 0.9 ml of samples at a flow rate of 1 ml per minute, basically you only need 0.9 minute to completely loading your sample into the cartridge. But you have a 3-minute loading time, so what happens to the next of 2.1 minute? So the 2.1 minute is actually washing those interference out from your SPE cartridge. Okay, next step of course to check for the linearity, precision and sensitivity of your method. So what we have tried over here in URI, we have tried online SPE with this PPCP compound and it works well. And just to show you, this is in a seawater sample matrix. We can see a good reproducibility at 50 ppt. Basically, you can see that the retention time and also the area counts are reproducible. Okay. And then we also calculate the recovery of online SPE for those 18 compounds, and it's not bad. We have most of the compounds have about more than 50% recovery. How about the matrix defect? Okay, in this graph actually there are a few things that I would like to say is that first thing, we have 18 compounds, right? And you can see for the blue color ones, these are basically wastewater, the dark blue. The lighter blue will be a wastewater diluted 10 times. And then the orange color will be a seawater and also seawater diluted 10 times. Sludge and sludge dilute 10 times. So this graph is to show you that at a different sample matrix, you will actually have a different matrix defect on all compounds. Yeah. Then, very important to note is that in this example of the blue color one, so I'm comparing the wastewater and a light blue of wastewater dilute 10 times. You can see that after I dilute the wastewater 10 times, the matrix effect is basically lowered by a lot. So it improves the analysis. But then you may think that, so if you dilute your sample 10 times, then isn't it you won't be able to see your sample if the concentration is too low? Since you have diluted 10 times, then your analyte will be also diluted 10 times. But actually this is not always the case, because the matrix effect will cause a lot of signal suppression. Signal suppression means your sample, you should be able to see at let's say 2 ppb, but because of the suppression, you are not able to see. And just another note in here is that those graph over here, which has a positive value, it shows a signal suppression, where those at the bottom and the negative value, it shows a signal enhancement. So just to say that for most of the cases, those heavy sample metrics will actually cause a signal suppression. Okay, now just to show you an example of wastewater without dilution and after dilution 10 times for this compound carbamazepine, which is also detected in wastewater in ABC. So the blue color one is actually a 20 ppb of this compound in wastewater. And then the same sample I have diluted 10 times. So because of the 10 times dilution, the CBC concentration is actually only 2 ppb. But in this example over here, you can see that even at 2 ppb, because we have reduced the matrix effect, we are able to see a better peak with a higher abundance. The next example on triclosan is also detected in our own UV samples. So basically the red color one, this red color over here is a 20 ppb triclosan in wastewater, and then we proceed to dilute 10 times, so that we'll get 2 ppb of this triclosan in wastewater, and we could see that we can get a higher abundance and a better peak shape for this compound. Of course, it's not the case for every compound, but what I'm trying to say that it does help to dilute your sample 10 times because it will really reduce your matrix effect. Okay, this is just an example of what we have done with 158 pesticides. So we use online SPE, and we could able to detect the pesticides at a 5 ppt concentration. So what is the advantage of online SPE? It's fully automated, coupled directly with the LCMS, so it will eliminate the human errors, and it's high throughput, effective and reliable to measure a range of analytes, which we have tried over here for these analytes. And it's relatively low solvent consumption, and of course we can reuse the online SPE cartridge for a few hundred of injection. And again, it's automatic, so we don't have to be there. The instrument and the software will do the online SPE for us. Okay, so it sounds like online SPE is very good, right? Then why do we do the manual SPE? Of course, there's also a drawback for this online SPE. Okay, the most important drawback would be it is not that flexible. So if you remember, I have recommended one method with MTBE just now at the first few slides. So we cannot use MTBE over here. So that means direct transfer of the methods from manual SPE to online SPE will not be possible, because it really depends. The solvent choice and the modifier that we can use in online SPE will be limited. It must be compatible with the HPLC itself and also the LCMS. So not everything can be used for online SPE. However, of course, online SPE still come with a lot of good advantage, fully automated, reusable, and high throughput. But in that case, please don't forget that manual SPE do have some, depending on the application that you are trying to do, online SPE will have some advantage as well, because it can also be optimized for optimum recovery, and we have a variety of device formats and the solvent chemistry. Of course, it will take some time to develop and optimize the protocol, and it may be costly and time consuming. But basically, both methods work well for our sample, and you really have to see what kind of analytes, what kind of sample that you want to detect over here. Okay, so what are the common issues that we actually encounter in this SPE or online SPE? First would be the poor recovery. So if you encounter a poor recovery, right, you can try to perform SPE for pure standards, and then you collect the washing step. Then you analyze by LCMS. So you need to check whether there's any breakthrough during the washing step. If you analyze breakthrough, your recovery will be lower. Then you can try to do a SPE with a different size of solvent bed mass. That means the packing material. You must make sure that the packing material has enough capacity to interact with your sample. Because you must also remember when you load your sample, not only your analytes will interact with the packing material, but also the interference. So the interference will also interact with your packing material. So proper size of the solvent bed mass is important. And then you have to evaluate your solvent elution strength. After that, you can try to change different types of cartridge. The next one under recovery would be you need to check whether there's any secondary interaction. So secondary interaction is something like this. In this example, what we want is the interaction of this compound over here, the methyl group, with the alkyl group of the packing material. However, there is a secondary interaction over here of your acid group with a silanol. So because of this secondary interaction, when you do the elution, you may get a lower recovery because it's difficult to elute this compound out from your SPE cartridge. So what you do is you try to reduce the solvent pH. So you introduce some protons over here to interact with the silanol. So once the silanol is being protonated, the secondary interaction will be released and you should be able to elute your compound of interest and get a higher recovery. Okay, how about a reproducibility issue? Maybe sometimes it could be a human error. So automated SPE or online SPE may help to solve this issue. And what about sample extract not clean enough because of the matrix effect? So as I say, you can try to dilute your wastewater samples 5 to 10 times before the SPE or non-SPE. And you can try to use the internal standard isotope labeled standard to correct for the matrix effect. Okay, this is my last slide. So in summary, what is the importance of sample preparation? Basically, we need to concentrate your samples to get to a lower detection limit, and you need to make your samples more compatible for the separation and detection. Solvent switch, our sample is aqueous, so it's better to switch it to organic. And then we have to try to eliminate or at least reduce the ion suppression or enhancement effect in LCMS analysis. Thank you.